Good morning, everyone. This is a short lecture on arithmetic of complex numbers. This deck of slides was prepared by Professor Art Magabo back in 2001. But allow me to present this as a quick lecture today. If you have done complex numbers back in high school, you can skip this video. But if you haven't done maths and complex numbers before, then this is the shortest video that we can come up with, just to keep you up to speed with what's required in this course. So let's proceed. So complex numbers are numbers that consist of a real part and an imaginary part. So the example here is complex number A with real part small a and imaginary part small b. The imaginary part is actually equal to the square root of -1 times that number over there. You must have heard this before as small letter I, imaginary number. But in electrical engineering, I is reserved for currents, so we use J instead. So this complex number A equal to A plus JB is a complex number with the real part and imaginary part. Of course, an easy example for that is given as letter A here, capital A, which is 3 plus J4. We say that this complex number is in its rectangular form because it's written in the rectangular coordinate system. Let's look at that. So this is a complex plane, which is a Cartesian coordinate system with an abscissa for the real axis and the ordinate here for the imaginary axis. So complex number A, which we met earlier, can be plotted on this plane with 3 as the real part and 4 as the imaginary part. So that's 3 plus J4. We can now locate A along this plane. You can imagine other complex numbers that can be located on this plane as well. It could be complex number B with a real part but no imaginary part. It could be complex number C with an imaginary part but no real component. It could be complex number D with a positive real part and a negative imaginary component. It could be complex number E with a negative real part and a positive imaginary component. And then complex number F with both real and imaginary components negative. So we say that any complex number can be located along this plane. Any complex number can be represented as a sum of its real part and its imaginary part. But there's another way to represent our complex numbers. So we can represent it in its polar coordinate form. This time, we include the magnitude and the angle of the complex number. Let's look at it this way. So we still have A is equal to sum of real part and imaginary part B. And we can still plot it along our Cartesian coordinate, real axis on the real horizontal axis, imaginary component on the vertical axis. That's the components. And that's point A there. And we can draw a line from the origin to that complex number, point A there. We can describe its magnitude and its angle between that ray there and the real axis here, angle theta. So we're saying that the same complex number A can be written in terms of its magnitude and its angle. Of course, we can use Pythagorean theorem to relate the components together or the descriptions together. The magnitude A can be written in terms of small a and small b using Pythagorean theorem. The angle theta there using your tangent function can be written in terms of b and a as well. So we say that complex number A, which can be written as A plus JB, can likewise be written as magnitude A, angle theta. This now is our polar form for our complex number. So in summary, Every complex number can be written in two forms, the rectangular form here or the polar form here. In the next few slides, we now proceed with the arithmetic of these complex numbers. We'll do addition, subtraction, multiplication, and division. So let's proceed with addition or subtraction. So we recommend that addition or subtraction be done in the rectangular coordinate form. I think that that's the most basic way to represent these numbers anyway. So suppose we have complex number A given as A plus JB and complex number B given as C plus JD, then we can add the two together, A plus B, simply by adding the real components together and the imaginary components together. So we don't mix them up. We can add the real components together and we add the imaginary components together. In the same way, you're going to subtract A and B or B from A. Then we subtract the real components, subtract the real component of B from the real component of A, and we'll subtract the imaginary component of B, which is D, from the imaginary component of A, which is B. So that's basically it. Collect the real components and collect the imaginary components. Here's a quick example. Suppose capital A is 8 plus J6, capital B is 4 plus J10, A plus B is simply equal to the sum of 8 and 4 there, plus J, sum of 6 and 10. We have 12 plus J16. We're going to subtract B from A. So this should be the difference between the real component, the difference between the imaginary component, and then we write them this way. We write them out this way, 4 minus J4. I hope that's easy enough. For addition and subtraction, collect the real components together, collect the imaginary components together. Let's move on to multiplication. Of course, we can also do multiplication using the rectangular coordinate form. So let's start with that. So again, we can have capital A, complex number A as A plus JB, and capital B, C plus JD. But likewise, we can represent A in its polar form, magnitude of A, angle theta A, and B as magnitude of B, angle theta B. So there are two ways to represent these complex numbers, but we start with the rectangular form this time. So again, the product of AB is simply equal to A plus JB multiplied by C plus JB. Of course, you know the maths here. You can simply distribute this together, do the happy face, and you have this long expression here, product of A times B, A and B, we have this. But wait, we have a J squared here. By definition, J is equal to the square root of -1. Therefore, J squared is equal to -1. So this component here is actually a real component. So AC and BD are both real components here. JAD and JBC are both imaginary components here. So we collect them together, and that should be our product between A and B. That's not too bad. However, there's a simpler way to do this. Suppose we do the multiplication using the polar form. So A is magnitude A angle theta, B is magnitude B angle theta. The rule here is multiply magnitude and add angles. We're not deriving anything this time. Of course, we can find references that will show the derivation. But we'll just follow the rules, and eventually we will show that it's equivalent to what we had earlier. So simply put, you grab these magnitudes, multiply them together, you grab these angles, you add them up together, and that's the product of A times 2. Let's see an example. So suppose we still have the same numbers earlier. Capital A is 3 plus J4, which can be written in polar form as 5 angle 53.13. Complex number B is 4 plus J3, which can be written as magnitude 5 angle 36.87. Let's multiply them together in rectangular form. That's 3 plus J4 plus 4 plus J3. This times this is 12. This times this is J squared 12. And then that's J9 and J16 for the middle terms. And then we add them together, and we get J equal to 25, which is equal to 25 angle 90 degrees as well. Again, that J there corresponds to an angle 90 degrees in polar form. Let's try this using polar forms. AB is simply equal to the product between the magnitudes. It's 5 and 5 over there. It's 5 and 5 there. And the sum of the angles. That's 53.13 and 36.87. Add them up, that's angle 90. Notice that they are the same, they're equivalent. So without deriving anything, we just showed it using an example. We say that when we're multiplying two complex numbers, we'd rather do it in polar form, multiply the magnitudes, then add up the angles. That shouldn't be too bad. Before we proceed with division of complex numbers, let's introduce another concept, which is the conjugate of a complex number. So by definition, the conjugate of a complex number is defined this way. So if the complex number is A, that's A plus JB, or A angle theta, the complex number A conjugate is simply equal to A minus JB, or A angle negative theta. In the figure, it looks something like this. If that's your complex number A along the Cartesian plane, A conjugate is located right down here. The imaginary component is now negative. The angle is this time negative as well. The real component did not change, the magnitude did not change. So that's the definition of our complex conjugate of a complex number. So let's try an example again. So the early example of A, 3 plus J4, or 5 angle 53.13, the conjugate of which is 3 minus J4, or 5, copy the magnitude, negative of 53.13. For complex number B, na minus 4 minus J3, the conjugate of which is 4 plus, minus 4 plus J3, it's 5, negative of 143.13. So that's the definition for the conjugate of a complex number. And now we're ready to proceed with division of complex number. So division of complex numbers can be done using rectangular or quadratic polar form, either way. But I guess you know where it's going. It's actually easier to do it in polar form. Let's start with rectangular form. So A in rectangular form is A plus JB, B is C plus JD. We divide these two together. If you're familiar with the maths here, you would like to rationalize the denominator here. So you multiply it by C minus JD over C minus JD. Okay? If you multiply these two together, you now have a purely real number on the denominator. So you do the maths. It's not too hard to do this. So the denominator becomes C squared plus D squared. That's now a real number. So the denominator is now a real number. You simply collect the real components, divide by C squared plus D squared, collect the imaginary components, divide by C squared plus D squared. This now is the ratio between A and B. It's not too bad, it can be done, but as you can imagine, it should look easier if you do it in polar form. So in polar form, that's A, magnitude of A, angle theta A, divided by B, magnitude of B, angle theta B. The rule is we divide magnitude and subtract angles. So the ratio should read as A over B, angle theta A minus theta B. Let's say an example. So the complex number A is 3 plus J4, which is 5 angle 53.13. Complex number B is 5 angle minus 36.87. To get the ratio, that's 5 divided by 5 is 1. This minus negative of 36.87 is positive 90. So that's 1 angle 90 in polar form. In rectangular form, real component is 0, imaginary component is 1. So we're not proving anything anymore. We're just showing the easy way of getting the ratio between two complex numbers. We use this rule here. Magnitude, you divide them. Angles, you subtract from each other. So we've done all 4 basic operations: addition, subtraction, multiplication, and division. The next couple of slides will just show a very quick introduction on how this is applied in electrical engineering. So here's a Phasor transformation. So basically, we say that if we have a sinusoid here, a sinusoidal function described by this cosine function, it has an amplitude f sub m, it has angular frequency omega, and a phase displacement alpha. We can transform it, the corresponding phasor, with a magnitude here and an angle here. So take note of the notations. This one is f of t. This is a time varying function. It's a function that varies sinusoidally in time. We represent it as small letter f in terms of t. We now transform it into a phasor. We sometimes refer to this as the same signal in frequency domain. So that's capital F there, with a j omega as the argument. That omega there is the angular frequency there. And we say that we can represent it in the phasor form or in complex number form, magnitude and angle. Of course, this looks familiar. This is the complex number that you just learned earlier. So what we're saying here is, in electrical engineering, every time you see a sinusoidal function like this, a time varying function, we can represent this as a complex number, as a phasor. Let's put an example. This is your time domain signal 311. That's the magnitude. That's the amplitude. Cosine 3770 plus 60 degrees volt. This is actually a voltage signal in volts. On the other hand, we might have a current signal in phasor form. It's really a complex number 10 angle 20 degrees in amperes. We can transform this, take this phasor form, we can transform this back to its time domain form this way. So that 311 becomes 220. That's actually 311 divided by square root of 2, 220. Grab the angle there, that's the angle of your phasor. So this time domain signal here can be represented as a phasor in complex numbers, 220 angle 60 degrees. Similarly, this is a phasor complex number. We can transform it back to its time domain form. What do? We write it as a cosine function. The angular frequency is implied. We grab the angle, we put it there. We grab the magnitude, but we have to multiply it by square root of 2. Notice that there's a square root of 2 coefficient there. So 10 times square root of 2 is 14.14. So the time domain equivalent of this one is 14.14 cosine omega t plus 20 degrees amperes. So what are we saying here? And time domain signal here, that's a sinusoid, can be represented as a phasor in terms of complex numbers. If you have complex numbers, that can actually be transformed back to a time domain signal here. So that's the main idea. We only have 2 more slides left, showing basically the application for this in electrical engineering. This single slide here talks about impedances. There's a separate lecture on impedance, but this is just an illustration. So the ratio between voltage and current, which is not too different from your Ohm's law, is equal to the impedance here. Take note that V here is a phasor, I here is a phasor, Z here is a complex number. With the complex number Z here, you can write it in rectangular form. That's equal to the sum of the real component and the imaginary component. We call this R here the resistance, and this is the same resistance you're all familiar with. You call this X here as a reactance, and this is pretty new for many of us, but we'll provide an introduction to that reactance in the other video. So this is your complex number impedance, which is the ratio between the voltage and the current. V is in phasor form, represented as a complex number. I is in phasor form, also represented as a complex number. The ratio is just an impedance Z. You've learned how to divide two phasors and two complex numbers. You can write it as a rectangular form here, or sometimes you can write it as a polar form as well if you want. But the rectangular form is more descriptive. That's the resistance, and that's the reactance. This also has applications on power. So the product of voltage and current, as you learned before, is equal to power. But this time, V is a phasor, I is a phasor, V is a complex number, I is a complex number. Don't forget that there's a conjugate sign there. The product of two complex numbers is a complex number as well. And you can write that in rectangular form, real as imaginary component. This time we say that the product of voltage and current conjugate is equal to the apparent power S. The apparent power S has two components, a real component, real power, and an imaginary component, a volt-ampere reactive or reactive power. So these now are the three concepts for power. The real power that you're all familiar with, we now have an apparent power, and we now have a reactive power. So an example. So suppose you have the voltage 230 angle 0. Again, that's a phasor in polar form, and a current phasor in polar form as well, 5 angle minus 40. We're asked to calculate the impedance and the components of the impedance triangle, and we calculate the apparent power and the components of the power triangle. So for the impedance, we simply get the ratio between these two. Z is equal to 230 angle 0 and 5 angle minus 40. You divide the magnitude, that's 46. You subtract the angle 0 minus negative 40 is positive 40. This is our impedance in ohms, in polar form. We convert it to rectangular form, that's 46 cosine 40, that's 35.24. We convert it to, we get the imaginary component 46 sine 40, we got 29.57 ohms. That's the impedance, that's the resistance, and that's the reactance of it. We're asked to solve for the apparent power as well. So what we do, multiply V and I conjugate. So S is equal to voltage times I conjugate. Take note that the conjugate of I is equal to 5 angle 40. So that negative sign there disappears. Multiply this together, we simply multiply the magnitudes, 230 by 5, that's 1150. We simply add the angles, 0 and 40, that's 40 degrees here. That's your S in volt ampere in polar form. We get the components, that's 1150 cosine 40 is 880.95 watts. The imaginary component is 1150 sine 40 degrees, that's 739.21 VARs. That's the apparent power, that's the real power, and that's the reactive power. So that's a quick introduction on how we use complex numbers in analyzing voltages, currents, impedances, and power. And we use that a lot in AC power systems. Thank you for checking out this lecture video.